This episode. Today we are going to look at different characteristics of the E8 lattice. So we tested 270 different projections of the E8 crystal. So 270 different angles of looking at this 8-dimensional structure. Each one of these gray dots. So we're looking at this figure. Each one of these gray dots is a projections that failed our statistical test. And these four red stars are the ones that passed every test we threw at them. But here's the question we haven't answered yet. Why these four? Is there something structurally different about the way they project the crystal into 3 dimensions? Or did they just get lucky? To answer this, we computed 25 different structural measurements for each of the 270 projections and mapped them into this landscape. So what you're seeing is the kind of fingerprint space. Similar projections sit near each other. So now we look at the red stars pointing at seed 3, 48 and 85, clustering here left, and then seed 46 is is on the right, sitting at the right. So we noticed 3 of our confirmed projections cluster here on the left. They share structural similarities, but seed 46 are ultra precision projections, sits way over here. So the confirmed seeds are not just copies of each other, they have something in common, but they're not identical. To find out what they share, we need to look deeper at the individual dimensions of the E8 crystal. So that's what we're looking at, a different layer called the Equalizer. So this is gonna reveal the dimensional fingerprint. So we use the Equalizer analogy to make 8-dimensional accessible in a way. So let's have a look at this figure. Confirmed seed matrices. Okay, this is confirmed seed matrices. So it's a 5-panel heat map with bar charts. Here is how each confirmed projection treats the 8 dimensions of the E8 crystal. Think of it like an 8-channel equalizer on a stereo. So each projection turns the volume up or down on each of the 8 channels. So the bar chart at the bottom, if we look at the bottom, show exactly how loud each channel is. So we have seed 3 for the left, seed 46, 48 and 85. So now if we look at the channel 2, the third bar, in seed 3 it's the tallest, so number 2, dimension 2. In 46 it's the tallest by far as well. In seed 85 it's one of the tallest. In seed 48, so which has a different stronger channel. Channel 2 is still in the upper half. Now look at channel 4, the 5th bar. In seed 3 it's the shortest. In seed sorry, it's seed 85 is the shortest as well, number 4. So 3 out of 4 confirmed projections have channel 4 as their weakest dimensions. So that's interesting to see. They share a common metric, which highlights or point to something structural. So every projection that successfully aligns with sacred sites boosts channel 2 and suppresses channel 4. So there's this strong common dimension for dimension 2 for the across the seeds, the confirmed seeds, and channel 4, which is the dimension 4, is the weakest. So it's like discovering that every song that sounds good in this room needs the bass up and the treble down. So the room, in our case, the geometry of Earth's sacred sites has a preference. So now we're going to look at a different figure, which I call dimensional correlations. So let's have a look. Dimensions correlations. So we're looking at the bottom left of this figure. So we have recurrence bar. So this chart makes the pattern unmistakable. The blue bar going up show how many of the 4 confirmed projections have each dimension in their top 3 strongest, and we can see number 2, dimension 2, is the strongest. It's in the top 3 for all the 4 confirmed projections. A perfect 4 out of 4. So dimension 4 is in the bottom 3. Okay, dimension 4 is in the bottom 3 for 3 out of 4. So this is the fingerprint. It is again number 2, dimension 2 strongest, dimension 4 weak. So let's zoom to the top left now. So there is grouped bars, and when we look at all 5 projections side by side, the 4 confirmed ones, and the 1 suggestive case, which is seed 166 in purple, you can see how each one handles the 8 channels differently. The confirmed seeds all share this pattern of strong dimension 2 and weak dimension 4. But they vary in the other channels, and that variation is what gives each one its unique character, breadth, precisions, or ultra precisions. This is a good moment to slow down and let the visual sink in. Okay, so now we're looking at another layer. I call it the inverted fingerprint. And so the goal is to validate the fingerprint using seed 166 as a natural negative control, then present the statistical evidence. So again, if we look at this part of the figure, top left, so we can highlight seed 166, which is a suggestive seed, not a confirmed one. So now here is where it gets really interesting. So we found a fifth projection, seed 166, that almost passed our test, but its raw statistical score was 0.015, so which was very close, but it failed when we corrected for multiple testing. When we looked at his fingerprint, we found the exact opposite pattern. Dimension 4, right? If you look at dimension 4, the channel that should be quiet is actually the second strongest. It's actually the strongest here for seed 166. And for dimension 2, the carrier that should be loud is weak. It's the inverted fingerprint. So this is like the control experiments that proves the rule. When you flip the equalizer settings, when you boost the channel that should be suppressed and suppress the channel that should be boosted, So the alignment breaks with that particular seed. So not completely, but just enough to fail the statistical threshold. So that's an interesting point. So now we're looking at another figure called feature importance. So feature importance, yes. Right, feature importance. So when we train a machine learning model, a random forest, to figure out which structural properties best predict whether a projection succeeds, the z-axis anisotropy came out on top. That's a measure related to how the polar regions of Earth are handled in the projections. The raw balance comes next, and how he basically tells us how evenly the 8 dimensions are weighted. So that came in second. And then you have matrix entropy, the overall complexity of the projection came third. So the machine learning confirms what we see in the fingerprint. It's about specific dimensional preferences, not about any single simple property of the projection. So now we are closing this episode with a last layer. I call it the preferred subspace of the E8 lattice. So I'm going to come back to PCA landscape. So we return to opening that image we had. So what does this all mean? The E8 crystal is 8-dimensional mathematical structure with 240 vertices and 6,720 edges. As you can see at the background, there's so many edges. Doesn't align with circuit sites from just any angle. It has a preferred subspace. Dimension 2 carries the signal, and dimension 4 blocks it. And dimension 7, we found this from a separate analysis of 130 competitive projections. It fine-tunes the quality of the alignment. So the successful projections are the ones that let the right dimensions through and suppress the wrong ones. And the one projections that invert this pattern, which is seed 166, is the one that comes closest to working, but ultimately fails. Out of 270 projections of the E8 crystal, only 4 find this subspace strongly enough to survive rigorous statistical testing. So the geometry is selective, and the selections has a structure we can now describe. So if you want to have a bit more information on what I've just presented, I am posting, and maybe today on the 16th of March, I will be posting my paper of the E8 lattice alignment with circuit sites. So that's the PDF here. So this paper will give you more information about the data, the results, and the methods I used to proceed. And if you are interested in downloading the paper, you can find it on Zenodo or Academia. Okay, so that's it for now, and this research paper closes the work I did on the E8 lattice aligned to those circuit sites 160 and 62 from the dataset of Ruber-Kuhn. My future investigation will be to synthesize E8 lattices which has a strong dimension 2 and a weak dimension 4, a particular subspace of the E8, and see if the results show a strong alignment with those data sets, because that's what the data has suggested. So it will be interesting to synthesize them and see if we can predict a strong alignment with these circuit sites. So that's the future investigation and the future work from here. Thank you for watching, and I'll see you for the next episode. Have a good day. Thank you. Bye for now.